So today we look at problem number 4 with 2025 Caltech Math Meet Final set of problems, the hard series. And this problem we chose to do it today because it borrows a lot from what we've done previously, and that is problem number 7. Um, we'll choose to be a little bit more detailed in our treatment of this problem. So if you haven't watched problem number 7, it's okay. We'll bring you along as well. So the problem is the definite integral from x equals to 0 to x tending to infinity of sine of the square root of 3x minus sine of x over square root of 3 all over x times e to the power negative x squared. Now, the answer that was provided in the problem is actually not correct. And so here we actually go ahead and provide the correct answer. So let's go ahead and solve this problem. So we'll begin in a kind of surprising manner. um, let's look at the numerator here, right? This numerator here is can be looked at as if you have an integral from beta equals to a to beta equals b of x times cosine of beta x, and you're integrating with respect to beta, then this is what you get: sine bx minus sine ax, right? So in other words, what we have here is the integral from t equals to 1 over root 3 to t equals to root 3 of x cosine xt. And we're integrating with respect to t, right? So this is very important, because then we can go ahead and instead of this expression, instead of what we have here, we can take this entire expression and plug in here, right? So that means that our problem now becomes a nested integral experience. So we have an integral from x equals to 0 to x tending to infinity of e to the power negative x squared over x times this portion here, the numerator here, which we eventually now will substitute with the integral we have here, right? And so what we see here is that since here we're integrating with respect to t, in this domain, this guy, the x component, can actually shift inside here, right? Or this x can also shift out here, and so what is vital here is for us to now see that our problem now has become a nested integral of e to the power negative x squared over x times x, and this x is cancel, times cosine xt. And we're integrating with respect to t before we go ahead and integrate with respect to x. But as we know, with this double integrals, we can flip. We can take t out and bring x in, right? And so what we're going to do now is we first of all have the integral of e to the power negative x squared times cosine xt with respect to t, and then with respect to x, and then we can now bring the t domain out and then begin with the x. So this is where we can now borrow from what we looked at previously in problem number 7. And so let's just highlight that integral, the integral from x equals to 0 to x tending to infinity of e to the power x squared times cosine xt. And we're integrating with respect. Let's this integral here, let's take t to be a parameter, right? And if this is a parameter, we're going to call this integral it. Now here we're going to use a Leibniz integral rule, which states that if we differentiate the integral with respect to x, the integral if we differentiate respect to x from the integral from t equals to ax to bx of fxt, this is what you get, right? But if if these are constants, then these portions just go to 0, and you have now an integral of the partial derivative of the integrand. And that's what we're going to use here. This idea was actually made really popular, and Feynman talks so passionately about it in his books. But let's not dwell on that. So if it is equals to this integral, then it means if we differentiate it with respect to t, then we're going to have to integrate the partial derivative of the integrand here with respect to t. And that means that we just have to integrate e to the power negative x squared times the partial derivative of cosine tx, which is negative x e to the power negative x squared times sine tx. So the important part here is that our derivative is the same as, this portion here is the same as the derivative of, with respect to x, of half e to the power negative x squared. And here we can now go ahead and use integration by parts to solve this. If that is our problem, what is integration by parts? Integration by parts says that if you have a product of a function v and a derivative of a function u, if you integrate that product, then the answer is uv minus the product of function u and the derivative of function v. So here we have this as our u and this as our v. So our uv is a half e negative x squared sine tx, obviously the limits are shown here, and then minus u, which is half e to the power negative x squared times the derivative of sine tx. So we get what we have here, but then if we try to evaluate this, we have limit as x tends to infinity of a half e to the power negative x squared sine tx minus limit as x tends to 0 of half e to the power negative x squared sine tx. Now we know t lies between 1 over root 3 and root 3. So it is a real number, and it's a small positive real number. So in other words, as x tends to infinity, this part tends to 0, but this oscillates between -1 and +1. So this entire part goes to 0, and this part also goes to 0, right? And so our derivative with respect to t of I is negative t over 2I. And so we can now rearrange things. So we have di over I. First of all, looking at this differential equation, it yields this equation where we can now integrate both sides, and we have natural logarithm of I being equal to negative t squared over 4 plus c. Raising this e to the power log I, e to the power whatever is on the right hand side, we have I is equals to e to the power negative t squared over 4 times e to the power c, which is the same as it being equal to e to the power negative t squared over 4, and this e to the power c can be taken as a constant c1. When t is 0, that means that it's the constant c1, which is the integral from x equals to 0 to x tending to infinity of e to the power negative x squared dx, which is root pi over 2. And that means that our problem it is root pi over 2 times e to the power negative t squared over 4. So our problem initially is this, which is the integral of it from t equals to 1 over root 3 to root 3. And so we can plug in place of it whatever we have here, which is root pi over 2 times e to the power negative t squared. We can take this out since it's a constant, and now we are left with the integral from t equals to 1 over root 3 to t equals to root 3 of e to the power negative t squared over 4. If we say let u be equal to t over 2, that means that 2 du is equals to dt, right? And then what happens if this is t and this is u? That means that when t is at the lower limit 1 over root 3, it means u is t over 2, which is 1 over 2 root 3. And when t is root 3, this means that u is root 3 over 2. So using this as the limits and then rearranging things here, what we will get is that our problem becomes pi over 2, root pi over 2 times the integral from u equals 1 over 2 root 3 to u equals to root 3 over 2 of e to the power u squared times 2. So this cancels out, and we have root pi times the integral from u equals 1 over 2 root 3 to u equals to root 3 over 2. So this here is a Gaussian function, and we know that ex squared dx is equals to a half root pi error function of x plus c. So using this, we're just going to now put root pi times half root pi error function u with the limits applied appropriately. So that means that our answer is pi over 2, because this root pi times this root pi, because pi over 2 error function of root 3 over 2 minus error function of 1 over 2 times root 3. So our problem, integral from x equals to 0 to x into infinity of sine root 3x minus sine x over root 3 over the sine x over root 3 over x times e to the power negative x squared is pi over 2 times error function of root 3 over 2 minus error function of 1 over 2 root 3. So thank you so much for hanging out with us. This has been an absolute pleasure solving or looking into this problem. If you haven't subscribed to our channel, we do really encourage you to subscribe to our channel. We would really appreciate your help. Just help us gain that visibility. If you would feel inclined, please share our videos here at Everyday Mathematics. What we do is we do enjoy solving these intricate math problems. And so we hope that you share this passion with us. Until next time, bye bye. Tutalu hala prochaine fois.